Hello everyone and welcome to my lecture series on molecular dynamics. So today is our first technical session and we are going to start with the classical equations of motion, right? So uh, first question we need to address is that why we need to use classical molecular dynamics, right? So now you should have noted. This is the first question that we need to address. Why we need to use classical molecular dynamics, right? So you might have uh, you might have noted that I am using this term classical to denote my MD. So why is that we use this adjective classical when we refer to molecular dynamics simulation? Well, there are two reasons. The first reason being, in MD simulations that are of biological interest, the particles are treated as classical objects in physics, and these classical objects represent more or less like ball and stick model, where in this ball and stick model the atoms are represented by these soft balls, and these bonds are represented by these elastic bonds as such. Okay, so we consider the bond as elastic because these bonds can stretch so that the distance between the atom can vary, it can increase or decrease. So since we use this classical objects in physics for representing the particle representation of our system in proteins, we usually refer to it as classical molecular dynamics. And the second reason being, the laws of classical mechanics will eventually define the dynamics of your system, and this is what we are going to learn in next few videos, as what are the laws that would define the dynamics in your system and how do we calculate them. Well, another approach is referred to as quantum molecular dynamics, where the quantum nature of chemical bonds are taken into consideration. So this quantum nature might include the electron densities and stuff like that when we talk about the quantum nature of the chemical bonds as such. Okay, so most of the time in our subsequent lecture we are going to deal with this classical molecular dynamics. Okay, why? Because usually we use classical MD when we want to simulate our biological process. Okay, so now since we are talking about these biological processes have two main features of biological processes. Okay, so the very first and important feature being that the in biological world the environment usually play a very relevant role in this process. Environment play a very relevant role in the biological process. Well, by that I mean that we have to include thousands to even millions of atoms in our simulation, right? For example, we need to simulate some protein that is in complex with water and ions, and that would eventually result into a very huge system that I have already shown you in my previous introductory lecture series, right? So I mean, it is not only the protein that will do things, but how that protein is surrounded by water and how that protein is surrounded by ions or lipid layers. Well, all those things would really matter when it comes to the biological processes as such. Okay, and eventually that would mean that we would have to include thousands to millions of atoms or particles in our simulation, right? So this is one of the very important feature of a biological system. And second important feature is that reactions in biological world are very slow. So the reactions that we are going to model are very slow. Okay, well, this is of course in comparison to a typical reaction that are considered in organic chemistry. The reactions in organic chemistry are very fast, and in comparison to the reaction that happens in organic chemistry, the reactions that would happen in biological world are comparatively very slow. Therefore, we need to monitor our system from a few hundred nanosecond. Okay, we need to monitor our system from the range of say some a few hundred nanosecond to even microsecond. Okay, so we need to simulate our biological system from 100 nanosecond to even microseconds, so that we can get relevant data to answer the question that we have set. Okay, so in short, what I mean is that we need to do a lot of energy calculation. Okay, we need to do energy calculations, and in future we would refer these energy calculation as to calculate energy gradient. Okay, so what we need to do for this microseconds to or even 100 nanosecond is that we need to do a lot of energy calculation, or in short we need to calculate the energy gradient all along our simulation for say for example many millions of times. Okay, as you know that when we compute one nanosecond simulation, we have to perform the energy calculation for thousand times. Okay, so what we call it as 10 lakh time, right? So since we have to do it for millions and millions time, well, a lot of energy calculation are needed to be performed when we kind of proceed for this molecular dynamics and simulation. Okay, so now in order to deal with all these prerequisite, we would need a method that should be the method should be very efficient, that can take care of all the millions of calculation, and at the same time it should be relatively accurate. Okay, and therefore we use molecular dynamics, and okay, therefore we use molecular dynamics, and in particular what we call it as classical molecular dynamics. Okay, so now this classical molecular dynamics is very useful to simulate biological processes. Well, some of the biological processes I have already mentioned in my previous lecture, like you can use such classical molecular dynamics on deciding as to how proteins acquire active and inactive state, or you can say how protein can transit between open or closed state. Okay, and how this transition happen. Remember that I have shown you that homoserine kinase trajectory. That particular trajectory is, classical molecular dynamics trajectory that can help you solve the question as to how protein can shift its transition from open and closed state or active or inactive state, right? Another trajectory that I have shown you, that consists of how the ions or molecules can cross across the membrane through those receptor. In this case, I have shown you how the ions cross that ion channel, and I have also shown you the trajectory that involves the passing or diffusion of glucose through GLUT transporter, right? We have also seen how classical molecular dynamic simulation can give you insights in how drug interact with a protein target, right? So all of these biologically relevant questions can be answered using classical molecular dynamics. Okay, so that is why we need to use this classical molecular dynamics in terms when it comes to when it comes to simulate biological systems as such. Okay, so now let us move on to our discussion to differentiate between what is small size versus what is large size systems. So this is a very important concept that should be very clear in your mind before we proceed further. Okay, well, say for example, while performing MD simulation, we what we actually do is that we solve equations to simulate these very large system that we are talking about. The system that might consist your protein that is surrounded by waters and ions and whatnot. And therefore, since we are dealing with very large system, it is very important to differentiate between the sizes as such, as to what exactly is small size and when is that we consider it as a large size system. Okay, so let us begin uh, with with consideration of a system that consists of only three atoms. Okay, well, say for example, consider our system that contains only three atoms. So this can correspond to your oxygen that is attached to hydrogen. Your water system now contains only three atoms and two bonds. Okay, now if we plot the energy of the system along the different state that this water molecule can take, well, the resulting plot, you can plot it something like this. Okay, over here on this y-axis, what we are doing is that we are trying to plot energy, or simply we can call it as potential energy. This term is also used interchangeably. So what we are trying to do is that we are trying to plot the energy on y-axis and the coordinate of this particular water molecule on the x-axis. Coordinate means what? This particular water, this particular atom in your water molecule will have some x, y, and z coordinate. It will This particular atom in your water molecule will also have some x, y, and z coordinator, while this oxygen atom will also have some x, y, and z coordinate. So what we are trying to do is that how the coordinate changes with time is exactly what we are going to plot. Okay, so we'll say for example, uh, when the when say for example, if the atoms in your water molecule are placed like this, then the energy can be over here. We'll say for example, can have some value. Okay, and as the atoms in your water system move, you can plot the energy diagram as something like this. Okay, so in this energy diagram, at this position, maybe your water molecule are placed at this particular distance. Okay, at this point, your water molecule can have this conformation. At this point, your water molecule can have this conformation. Okay, and we'll say, for example, at this particular point, when the energy is lowest, your water molecule can have this type of conformation. Okay, and we'll say, for example, if your water molecule has this conformation, it can have, say, some this value, and it can have, say, some this value over here, this value of free energy. If it has got this conformation, that is, the oxygens are, these hydrogens are placed quite far away from this oxygen atom, and it can have, say, something like this if these oxygens are placed quite far away. Like, what I want to say is that based on how the atomic position in your water molecule will change, it will have some associated free energy associated with it, and if you plot that free energy, you might get a plot something like this. Okay, so this resulting plot is usually termed as potential energy surface. So what we have drawn, we can call it as the potential energy surface of water molecule. Okay, or we can simply call it as potential energy surface, PES. So PES in further discussion would correspond to the potential energy surface, right? So uh, in this way you can obtain this potential energy surface, right? Therefore, such potential energy surface describe the potential energy of your water system, especially a collection of atoms in terms of the Cartesian parameters, x, y, and z coordinates. Okay, so normally the position of atoms is described in terms of these Cartesian coordinates. Okay, so this is, in short, a typical potential energy surface plot of water. Okay, now what can we observe from such potential energy surface of water? Okay, so in this potential energy surface, we can clearly define a global minimum point, or what we call it as a, this is called as a global minima. Okay, you can observe a point in at which there is usually a lowest free energy or lowest energy in your water system. Okay, so we can clearly define a global minima in our potential energy surface, or we can say there is a well defined minimum in water's potential energy surface, right? What we can say is that there is well defined energy minimum in water's potential energy surface. Okay, so in other way around, we can also say that most of the time when our water molecule is observed, okay, most of the time our water molecule will have conformation that would lie around this particular surface of your energy minima, or you can say potential energy surface. Okay, so especially around the global minima. So very less time it would happen that the structure of water molecule would appear something like this, or very less time it would happen that your structure of your water molecule might look something like this. Most of the time your water molecule will have conformation that can be located in this particular energy surface or this particular region of your potential energy surface, right? So this is what we can infer from such potential energy surfaces as such. Okay, so uh, so when we simulate such small system, okay, or when we simulate any system, what is our interest is that we are generally interested in, say, finding out some property of our system. Okay, for example, one might be interested to monitor how energy changes all along the potential energy surface during the simulation, right? So in this case, the property of interest might be the free energy that we were talking about. Okay, and therefore when one simulates small systems like this, like water molecule, the approach is to find the minimal energy state of the molecule, and then compute the property of interest at this minimal energy state. Okay, so this approach will work very effectively only when one can observe that there is a definite minima in the potential energy surface of the system, and the system thus is very small. Okay, so you can say that if there is a single energy minimum that is observed for any system, you can say that the system is a small system. Okay, that is what I want to say. Okay, so if you are interested in finding out some interesting property, and you can calculate this interesting property based on a single minimum, then you can consider that such systems are very small. Okay, so this approach of finding out the energy minimum and then finding out the property of interest, the value for your property of interest, this approach will work well only when we have one defined energy minima for that system, and the system thus can be called as a small system, right? Well, now things start to become complicated when we deal with large system like proteins, and when we deal with large systems like even simulating the nucleic acids in say some solvated states, that would involve a lot of atoms as such. Okay, so in such a case there will be a large number of minima in the potential energy surfaces. Okay, when when we deal with our protein and our protein in solvated system, you won't deal with, or it won't happen that you would observe a single minimum, right? You might observe that there are a large number of minima that your potential energy surface has when it comes to biological molecules or biological simulations like protein in water, ions and everything. Okay, so what I want to say that there will be a large number of local minimas that you might observe in a potential energy surface of biological systems. Okay, and most of such local minima are equally accessible by your protein water system, right? So this is called as the large system, where there would be multiple local minimas and you cannot define a single global minima. Okay, so now if we consider this as the potential energy surface for our protein molecule that is well defined in say some water box that I have already shown you, okay, in our previous trajectories. So in such you know potential energy surface of your biological system, okay, in this potential energy surface of small, you can consider it as a small protein molecule, then you can consider that this is local minima number 1, this is local minima number 2, this is local minima number 3, local minima number 4. Okay, and say for example, when this local minima is reached, your small protein might look something like this. Okay, when this minima is reached by your system, your protein can have this configuration. If the system reaches this particular energy minima, your protein can have this configuration, and similarly when your protein reaches this minima, your protein can have this conformation. So the conformation of your protein can be different when they reach different local minimas as such. Okay, so in other words, during the simulation that you conduct that involves biological system, our system can populate each of these energy minima. Okay, and in such situation, what we need to do is to sample all of the coordinate space that is involved in this much region. Okay, what we are trying to do is that what we need to do is that we need to sample this space of coordinate in order to find out all of these possible minima. Okay, all of these possible minima, and all of these minima that now we have minima number 1, 2, 3, and 4, all of these local minima will be relevant for computing the property of our interest of our system, right? So we would have to consider all of this conformation of our protein when it comes to finding out the property of interest of our system or free energy of our system as such. Okay, so now let us proceed with our further discussion as to what exactly we do. Okay, so well, say for example, let me again draw a bigger potential energy surface of our protein molecule now. Okay, on this y-axis we would be plotting our potential energy or just free energy of our system, and on our x-axis there would be coordinates, or you can say conformation of our protein. Okay, and if we plot the potential energy on with respect to the coordinate, you can expect to get such graph of potential energy surface, right? And again we have this local number of local minimas that are equally accessible by our protein system. Okay, so now if we move with this particular potential energy surface, what we have to do in MD simulation is that what we do is to locate the minima in such potential energy system. This is one minima, local minima. This is another second local minima, third and fourth, and maybe fifth. Okay, so these are the possible local minima that your system can acquire. Okay, so the first minima that we obtain has, we'll say, configuration A. We would call this call this particular minima. Okay, and at this particular minima, our protein is, well, say, having this configuration, or you can say this conformation, to be very precise, CON conformation. We would call the structure or conformation of protein that correspond to this local minima as conformation A. At this particular minima, our protein might have some different conformation. We would call it as conformation B. At this particular point in our minima, our protein might move and might acquire some different conformation. We can call it as conformation C. Over here, it can have different conformation. We can call it as conformation D. And we can then have well, say for example, n number of conformation in our system. Okay, okay, so we can call it as conformation E, right? So this is what it is. uh, so for each conformation, then we go for calculating the property of interest, right? Well, so for example, the free energy that is associated with conformation A, we'll say for example the value of that free energy is A1 if free energy is what is we require for our protein system. Okay, free energy in our case is the property of interest. Okay, so what I want to say is that of these all possible local minima, each local minima will be associated with a conformation. Okay, we have named those conformation as conformation A, B, C, D, E and so on, and we are interested in calculating the free energy of our protein. Therefore each conformation will have some value for free energy for each conformation, right? So this is what it means. In this way we proceed to compute the properties of interest, that is free energy, for this conformation B. Okay, and say the conformation, the property of free energy when the protein is present in this conformation B is A2. Similarly for conformation C the free energy would be A3. For conformation D the free energy would be A4. For conformation E the free energy would be A5, and therefore we have a n number of free energies for n number of conformation that can be observed in our potential energy surface. Okay, so hence we proceed to find out all the relevant configuration that are present in your local minimum and compute the respective values for properties of interest, in our case that is free energy. So at the end we will have we might have found out several configuration, okay, in our simulation in our potential energy system. Okay, and we might have some associated value for their properties of interest, right? Well, say for example we have got, for conformation A, we have got property of interest value as A1, A2, A3, A4, A5 till AN. Okay, so now after we do that for each and every confirmation, okay, so after finding all the relevant confirmations and their corresponding value for properties of interest, then we proceed to compute something called as the probabilities to have each of the configuration. Okay, next what we do is that we compute the probabilities. Okay, now what probabilities do we calculate? We calculate probability to have each of this configuration. Okay, so what is the probability that my protein will have this conformation? What is the probability that my protein will have this conformation? Or what is the probability that my protein would end up in this local minima so that it can have such conformation? Okay, so this is exactly what we are doing. We have got say conformation A, and we have calculated the property of interest, that is A1 for free energy. Then we have got conformation B, which we know has got value of A2. For C we have got value A3. For conformation D we have got values A4. For conformation E we have got values A5, and for confirmation N we have got values AN. Okay, so now next what we do is that we calculate the probability. What is the probability which is denoted by, these probabilities are denoted by rho. Okay, so you can say that we have got rho1 as a probability of our confirmation to well, here you can say that rho1 is the probability of the protein to acquire the conformation A. Similarly, you have got row 2, which can be considered as the probability of protein to acquire conformation B. Okay. Similarly, row 3 would be considered as the probability of protein to acquire conformation C. Right? Row 4 would be the probability of this protein to acquire conformation D. Row 5 would be the probability of the protein's conformation, the probability of protein to acquire conformation 5. And similarly, we have got a row n that would correspond to the probability of your protein to acquire conformation n. Okay. So since after calculating this probability, what we can do now is that we can average these properties from simulation frames. Okay, so now consider that these are all conformations that are saved in our trajectory, right? So what we can do now is that we can average this property from the simulation frame, and in this way, average property that we obtain from simulation are conventionally written in such type of bracket. Okay, so whatever, if it is written in whatever property of interest is written in this bracket, in our case our property of interest is free energy, and if it is written in such a type of bracket, then you can consider them ki these properties are calculated from the frames from the trajectories, right? So the average property from simulation are conventionally written in this bracket. Okay, so when I write A in this particular bracket, that would mean that I am referring to the free energies that I have obtained by sampling the frames from the trajectory. Okay, and hence we can write the equation something like this, right? So what this would correspond, this is the average free energy of our protein ligand system or protein system in water along the simulation. Okay, and how can we average it? We can average it, or we can write it as we'll say, for example, row 1 A1 plus row 2 A2 plus row 3 A3 plus row 4 A4 plus row 5 A5, and similarly you can say row infinity and A infinity. Okay, so this is how you can sum average up the properties of interest value, in our case that is free energy. So how you can read this equation now? You can read this equation as the average free energy of protein all along the simulation is the sum of product of free energy in the conformation and the probability to acquire that conformation, right? This is what it means. Okay, so in this particular equation, okay, in this equation the average value of our property, that is free energy, is an ensemble, or is, you can say, simply is sum of each value of property of interest, okay, multiplied by the probability to acquire that particular configuration. Okay, and usually if we have very large amount of configuration to deal with, okay, so we'll say, for example, that is how we have written this infinity. Okay, that is represented by infinity in our equation. This infinity, what do this infinity say? That we are dealing with very large number of configuration, large number of probability, and large number of values that are associated with each confirmation. Okay, so in such case we can write this equation uh, in terms of integral as well. Okay, now let us represent the conformations by, simply small q. Okay, what we will do, instead of writing confirmation A, confirmation B, confirmation C, confirmation D, we would represent this confirmation as q. Okay, now if we represent the confirmation of protein by q, and we need to represent this particular situation with infinite number of possibilities, right? We can write this equation in term of integral. So all what we are trying to do is that we are trying to represent what is the probability of probability 1 multiplied by the property of interest 1 plus probability 2 to property of interest 2 plus probability 3 multiplied by property of interest 3, probability 4 plus property of interest 4, sorry, this is multiplied row of 5 into property of interest 5, and similarly probability infinity with a of infinity. Now uh, why we have considered it over here infinity? Well, if you remember that if you want to conduct a simulation of say only 1 nanosecond, you would have to consider sampling of how many frames? 100,000. Okay, so we'll say for example, if you are performing a 100 nanosecond simulation, this much number of confirmation you would have to sample. Okay, and simply you can consider, practically you can consider them as infinite. Therefore we have considered infinite probabilities and infinite configuration that infinite confirmations that we are supposed to sample. Okay, so if this is the situation, uh, you can write it in simpler terms using something called as the integrals. So you can write it as the integral of properties of interest with confirmation q dq. Okay, so this is how you write it in form of integral, but for that you would need this row q that would correspond to the probability distribution of the confirmations as such. Okay, so in this is a simpler way of representing this particular situation that we ended up with. Okay, so in this integral we have the term this row of q, okay, that correspond this row of q now correspond to something called as the probability distribution. Okay, this is how we denote things in calculus. Okay, so now this probability distribution pq, again this probability distribution of rho q can be calculated using this expression. It is exponent of the potential energy, this is capital V, okay, of your confirmation divided by kt. Okay, and it is to be divided by integral of exponent of energy of confirmation by T dq. Okay, so the value of this probability distribution can be computed as exponential of energy, that is denoted by this capital V, of a particular configuration Q divided by the integral of all possible conformations that you might obtain. So this integral now defines this particular integral sign now defines the possibility of all configuration that you can obtain. Okay, so here this particular term, let us write it simply over here as the exponent of the energy of the conformation divided by kT dq. Okay, so this particular function, okay, is also called as the partition function. Okay, so in order to define the probability distribution, you would have to know something called as the partition function. Okay, so in short, if we want to compute an average value of free energy or the property of interest in a trajectory, which is denoted by this A, okay, we need to know the this probability. If you want to calculate the free energy, we need to know this probability. Probably what is the probability of particular configuration, and then the row of q that correspond to the distribution. Okay, and then dq. When we have integral, we have got dq in calculation. Okay, so this is what we need to figure out. Okay, so what do these equations say? This equation say that distribution, well, so for example, the probability distribution of system, right? So, and in order to compute probability distribution, we will have to compute the most important configuration. As you can see that this probability distribution cannot be completed without the important conformation of your protein. Okay, if not all of the important conformation, right? So we will kind of focus on most important conformation, if not all possible conformations, right? Therefore, we can compute such most important conformation that would correspond to the local minima, okay, by running a classical molecular dynamics simulation. Okay, and that is why, my friends, in order to sample the structural space, we need to run this classical molecular dynamics simulation, right? So this is what you are supposed to learn today. So well, what we have learned. Okay, so I have kind of explain you what are potential energy surfaces. Okay, secondly, I have explained you what are ensembles, and ensemble average properties. Ensemble means what? The the collection of frames in your trajectory might correspond to an ensemble. Okay, so what are ensembles, and how do you obtain some average properties from those ensemble or from those trajectories, right? Third, what we have learned is that what are probability distribution, Okay, so okay, so one more thing, that this expression rho of q is equal to this is also called as, this particular expression that we have derived, it is called as Boltzmann distribution. Okay, so the what you can say, the probability distribution rho of q, okay, that is very relevant in expressing this particular situation, is given by this Boltzmann distribution. Okay, so what are probability distribution and Boltzmann distribution? Okay, I told you what are partition function. Okay, and last thing that we have discussed is that what are the, you can learn mathematical implication of integrals and the Boltzmann distribution. Okay, so to define this n number of configuration or infinite number of configuration and the properties of interest associated with them, okay, and in order to sum up, or you can say to find out an average of all the properties of interest, you need to figure out the probability distribution, or what we call it as Boltzmann distribution. Okay, and you can represent this term in terms of this calculus as well. Okay, so well, now this is, you know, very basic concept of classical molecular dynamics. Okay, how your Boltzmann distribution or probability distribution is related to the number of conformation that your protein can acquire in your potential energy surface that you can obtain during your molecular dynamics simulation. Okay, so these are all basic relationships. So in our next lecture we would be dealing with the Hamiltonian equations and what are their roles in molecular dynamics and simulation. Okay, so see you guys in our next lecture video.